All right, so today we're going to learn how computers work. And I want you to all, your assignment for the week is going to be to share with somebody in your family or a friend. I want you to explain to them how computers work. So that's your assignment for the week. And when we explain what we're learning to others, it deepens our learning. So just take what you learn, share it with somebody else. And when we come back to class next week, I'll randomly call on people to then share back to the rest of the class, your understanding of how computers work. And so we're going to look at the highest level, most basic level, just like what is the theory behind how computers work. And so the ideas behind how computers work are very simple. It's really simple. But the implementation is incredibly complex. So it's a really simple idea, but it's really difficult to implement it. And so we're going to just learn the really simple idea of how computers work. So the first thing that you need to know, there's just like a couple of little steps that we go through when talking about how computers work. The first one is that computers run on electricity. So this is our fundamental base starting point. You're like a lawyer making an argument, and here are my points, and you got to have all these points to build up your presentation, your description of how computers work. So you need to nail all these points when I ask you to describe how computers work. Computers run on electricity. That's easy enough to remember, right? That's not difficult. And then number two, electricity has two discrete states. On and off. That's your second point. So how do computers work? Computers run on electricity, and electricity has two discrete states, on and off. That's pretty small up over there. What? What? If I have, so here's the next point in your presentation of how computers work. If I have one circuit, or you might also call this a switch, right? Like a light. Because a circuit, a switch, it's just like the lights in these classrooms. You can turn them on or off. I can store and convey two messages. And so here's an example. Porch light on Halloween. Porch light on Halloween. So if your porch light on Halloween's on, what's it in our culture? What's that mean? Yeah, I'm giving out candy, come on up and go trick-or-treating at my house. Now if my porch light is off, that means go away, I don't have any candy. So with a single circuit, a single switch, I've stored and conveyed a message. And it can be of one of two messages. Come trick-or-treat or go away. My porch light is on or off. Okay? And that is known as a coding scheme. I'll just write that phrase down here. Trick or treat. Go away. Okay? That's a coding scheme. So based upon the state of a circuit or a switch, it means one of two things. Come trick or treat or go away. Is that complex? No. It's totally simple, right? All you got to do is remember computers are like the porch light on Halloween. Really? Tell me more. Well, computers run on electricity. Electricity has two discrete states, on or off. If we have a single circuit or switch, we can store and convey two messages. Porch light's on, come trick-or-treating. Porch light's off, go away. Let's start scaling that up. I'll zoom in case you're watching this online. You can pause the video right there for a second. Just look at that. All right, let's scale that up. So just looking to see what colors I want. I think I want, I don't know. Black's easiest to read, right? Yeah. You want black. So one circuit equal two messages, right? What if I have two circuits, two porch lights? How many messages can I store and convey? 4. You guys are awesome. How'd you know that? Right? 4 messages. It could be both on. It could be both off. It could be left on, right off. It could be right on, or left off, right on. Right on. And then if I had 2 porch lights, I could create my own coding scheme and share that with my friends. So my coding scheme might be party's on. Both lights are on, party's on. Both off, sleeping. If the first one's on, the second one's off, that's studying. And if the first one's off and the second one's on, that's movie night. So now, as you walk by my abode, on your way to or from campus in the evening, you know exactly what state I'm in. And whether or not you could drop in and watch a movie with me, or study with me, or if you should just leave me alone instead of sleeping, or if it's party night. That's my coding scheme. It's based upon circuits being in a state of on or off. How many people are like waiting for the hammer drop? Like, when's it going to get complicated? It's simple in theory. It's complex in implementation. That's how computers work. We just keep scaling it up. And instead of saying on, off, like that, maybe I'll say, okay, I'm just going to abbreviate it because I'm tired of writing on and off. I'm going to say, okay, I'm just going to have this be, instead of 1, 1, instead of on, I'm going to write 1, 1. So I could also just go 1, 1. This party, this one's 0, 0. 0 represents off. This one's 1, 0. This one's 0, 1. Wait a minute. That's why you always see zeros and ones related to computers. Talking about things in on-off states. That's why when you look at this dog, not the best artist. Now it looks like it has hair. What is that?
On off.
That's on off. That's the power symbol. It's a 0 and a 1. Off, on. Whoa.
Is that really what that means?
That's what that means. It's awesome. Symbology, symbolism, emblem, imagery, and I don't know, iconography. It's awesome graphic design. The 0 and the 1 mean on off. So they use 0 and 1 to create the button, which allows you to turn it on off. Whoa. That's amazing. Now tell that story. It's not complicated. Right? Tell that story to your loved ones. There's some important pieces in that story. Computers run on electricity. Maybe start with, you know what, a computer's like your porch light on Halloween. What? Well, just like your porch light, computers run on electricity. Electricity can be on or off, just like your porch light. And just like your porch light on Halloween, if it's on, it means one thing. If it's off, it means another. Come trick or treat, go away. Same thing in computers. And we call those, we just have circuit switches in on-off states. And then we say if it's in a certain arrangement of on-off, it just means something. And we just create these coding scheme things that when we've stored circuits in a certain arrangement of on and off, it means this thing or it means that thing. Right? We just create our own coding schemes. So coding scheme is one of the important words you're learning. Coding scheme. Right? Circuit switches. It's just like a switch back there, man. It's a light switch. It's on or off. That's it. Create a coding scheme. Power symbol, 0 and 1, on, off. Instead of writing on, off, we write 1 for on, 0 for off. If we had 3 circuits, anybody have any commentary? You guys are like a really awesome and tuned in class. But talk a little too. Anybody have any questions or comments?
So I know that it means on or off, but when you're actually coding it out, how does it know what you mean specifically by it? Because you can make a lot of different, like how it's laid out, how it looks, how the page looks, and all of that.
Simple in theory, complex in implementation. Right, the most basic level, porch light. Man, we can control that. Single circuit on off. Everybody knows the coding scheme. Right? We don't have to have a monitor. We don't have to render graphics or render text to screen or get a printer to print ink in a certain way. Take those 0s and 1s and turn them into letters and print them on a page. Complex in implementation. Simple in theory, porch light on off. We know what it means. And when you program, you write in, there's different levels of language. There's machine language. There's assembly, which is a step above 0s and 1s. Machine language is just 0s and 1s. So that's another nice term. So when you just have 0s and 1s, that's machine language. So every computer is running with 0s and 1s. Just 0s and 1s. Machine language. And And then above that is assembly, which is the stuff above. And then third level, third generation languages, which are the programming languages we use so we can write words. And then we compile our programs down to zeros and ones. So it takes our words, our programming statements and expressions, and turns that into zeros and ones for the computer to run. And then fourth generation's like procedural structured query languages. And fifth generation is what we speak, which is natural language. And increasingly, computers are beginning to understand natural language. That's part of artificial intelligence. I could just talk to my phone, and it really does really great voice-to-text recognition. You could talk in different accents. You know, I could talk in my California accent, which doesn't sound like I have an accent. Or I could get in touch with the southern roots on my mom's side of the family, and I could talk with a little southern drawl. And I could say, y'all gonna come on over? Or whatever. I didn't quite channel that well enough, but you know, it figures it out. Pretty amazing. If we had 3 circuits, how many messages?
8.
What about if we had 6 circuits?
12.
No. So the formula is 2 to the n, 2 to the power of n, where n is the number of circuits. So if we have 1, it's 2 to the power of 1. If we have 2, it's 2 to the power of 2, which is 4. If we had 3, it'd be 8. If we had 4, it'd be 16. If we had 5, so this would be 8 messages that we could store. Here we store 4. This could be 16. This would be 32, right? This would be 64. So it's 2 to the n is what we're doing there, right? 2 to the n, 2 to the power of n. 2 to the 7 is equal to 128. 2 to the 8 is equal to 256. You know, and 2 to the 9 is equal to 512. And 2 to the 10 is equal to 1024. Those are starting to sound like computer numbers. 32, 64, 128, 256, 512, 1024, like, you know, they got a 64 gigabyte SD card in that computer. Yeah. What the heck? And the reason it's all kind of like 2 to the n is because it's base 2. So we use a base 10 numbering system. This is base 2. It's base 2 because electricity has 2 discrete states, on and off. We got 2 states, on, off, 1, 0. Right? These are binary digits. That is a binary digit. Okay, that 0 there is a binary digit. It's a digit and it's binary. Why do we call it binary? What's the prefix bi mean?
2.
2. Bicycle, 2 wheels. Biplane, 2 wings.
Only 2 numbers.
Huh?
Only 2 numbers.
Yeah, binary. So nary is maybe number, I don't know. But binary is two numbers, 0 and 1. And so when we talk about a bit, take the I from whichever side you want. A bit, right, is a binary digit. It's a single bit. It's a 0 or a 1. We learned coding scheme, power symbol, 0, 1, machine language, binary digit, bit. 2 to the power of n to figure out if I have 2 circuits, I could store 4 messages. You know what a binary digit, a bit is now? Zoom in on that for that home people.
So is that why they choose those numbers for the like storage spaces and stuff like that, like you said earlier?
That number for the storage
Like
spaces.
SD cards, for example, it's like 8 gigabytes and then it goes up to 16 and then 32. There's like no storage in between.
Yeah, because they're all somewhat connected to 2 to the power of n.
So then, like, when you're talking about RAM and processors, the, like, 512 i7 processor, that's because it has 9 separate circuits that all, like, connect, or?
Yeah, that's a great question. I don't know. Because like theoretically, you think they could probably say, oh, this one's going to be 67.3 gigabytes, right? And then we'll just create a circuit with that many things in there. So when we measure bits, and let's keep that in mind, we're going to learn about measuring bits. We have, in the beginning, there's 1 bit. And then 8 bits is equal to 1 byte, which is what we call it. And originally, computers operated, in small chunks, like a byte. And we'll just deal with 8. And so we had 256 messages we could store. And so the ASCII, American Standard Coding Interchange text something. ASCII was a text coding scheme which worked with 8 bits or a byte, and it could store 256 letters, lowercase a through z, uppercase a through z, some punctuation. But that doesn't help you if you're speaking Chinese or Japanese. So people got all these different coding schemes, and then you'd have programs in Japanese which wouldn't work in another version of Japanese, or Japanese stuff wouldn't work in Chinese. And so they increased that from 1 byte for text coding, encoding, to 4 bytes, which is UTF-8, which is now the world's most popular coding scheme for text. And with 4 bytes, we're dealing with 2 to the power of 32 in terms of the number of characters that we could store, which is huge. 2 to the power of 32. Anybody want to punch that in? No? It's 4,294,967,296. If you have 2 to the power of 32, it's like 4.2 billion, 4.267 billion things you could store, different combinations of 0 and 1. If you have 32 porch lights, you have 4.2 billion different combinations of on and off. Whoa. Right? But then the computer could look at that real quick and say, oh, that's this Chinese character here. Wow. And it took 32 circuits in an on-off state to store that. You hit that Chinese character, 32 circuits go in.